for chapter 13, which is called Mid-Latitude Cyclone Model 2. And so this is really a follow-up from chapter 12, where we really focused on vorticity and explaining the causes for regions of convergence and divergence in the middle and upper parts of the troposphere. The purpose of chapter 13 is really to focus on mid-latitude cyclones, which are just the technical term for a low-pressure system. So think about cyclones or low-pressure systems, and we distinguish between mid-latitude, which are low-pressure systems that we see in our part of the world, and tropical cyclones, which are tropical storms and hurricanes. So mid-latitude cyclones refers to low-pressure systems that occur in the mid-latitudes where we live. So what we're going to be doing in this chapter is we're going to be focusing on the life cycle of mid-latitude cyclones. Excuse me. So let me start the PowerPoint presentation. We are going to actually come back to some of the topics in chapter 12, some of the principles. We are going to look at vorticity again in this chapter, but now we're just going to begin to apply the concepts of vorticity that we learned in chapter 12. So you're going to see that in this presentation. So we're going to begin from the start, which is a good place to begin. And what we have here is just a figure from our textbook. And this is a figure of a stationary front, which is aligned parallel to a couple of surface isobars. And what you see basically is that we have clockwise motion on both sides of the stationary front. So we have high pressure centered to the north of this image, and we have clockwise circulation showing easterly flow to the south of the high. And on the south side of the stationary front, we would have a high pressure system that is centered to the south of the 1016 millibar isobar, and we would have westerly flow on the north side of that high. So what we see here is that we basically have parallel flow on both sides of this stationary front, which is why the stationary front isn't moving. The wind is not in any way kind of pushing against this boundary. So what we tend to see when we get the formation of low pressure systems at the surface is that cyclogenesis, or the formation of a cyclone or low, typically occurs along this kind of a stationary frontal boundary. And it also occurs beneath a region of upper level divergence. So we already talked about where we might find this upper level divergence in chapter 12. So it could be beneath a jet streak. So it could be beneath the right entrance or left exit region of a jet streak. Or it could be to the east of a mid-tropospheric trough and to the east of a vortmax, where we have decreasing vorticity and increasing divergence. So it could happen over in terms of a couple of locations above the location of this front, where the circulation in the mid and upper troposphere could actually cause divergence to occur. Typically, when we have this kind of a setup with a stationary front where the flow is parallel on both sides, what we often see is that we begin to get increasingly warm air to the south of the boundary and increasingly cold air to the north of the boundary, because the wind in no way at this point is transporting air with different temperature boundaries north or south. So the air masses are kind of just stuck in place, and so they become more extreme. And eventually what will happen in terms of the upper level flow is that we'll typically get some sort of a buckle in the mid-tropospheric or the 500 millibar pattern and the formation of a trough ridge system, which will then kick off an area of upper level divergence, and then we'll have the formation of a low somewhere along this stationary boundary. So here's how it would look once we get that buckle. So you can see we have a trough now at the 500 millibar level, and I've put in an X to indicate the location of a vortmax. So this would be where we would have our maximum in absolute vorticity, and then as the air blows parallel to the isoheight pattern, we would get decreasing vorticity to the east of our max, and then as vorticity decreases, we would get divergence, mass removal from the column, and then low pressure formation on the stationary front. And then going back to chapter 6, the counterclockwise and inward directed circulation would then lead to the movement of cold air to the south and warm air to the north, and then we would have the formation of our frontal boundaries, our cold and warm frontal boundaries. So again, I just have the same wording beneath that I had on the previous slide. So again, increasing north-south temperature differences result in the eventual advance of cold air to the south, and our 500 millibar pattern buckles. Now what I want to do next is I just want to take a look at a hypothetical low pressure system and the fronts that extend from it. And what we see here is what is typically apparent in the real world, and that is that we'll have a low pressure system. The cold front typically extends to the south and west of the low. The warm front typically extends to the east, northeast, or southeast of the low. So this is not at all uncommon, this particular model that we have in this figure. So what we have again is low, our fronts. This blue area indicates the location of what the book refers to as fresh cold air. So this is cold air that is typically advecting out of Canada, transporting out of Canada, and it is pretty cold. And then to the north of the warm front, we have retreating cold air, and the book refers to this typically as stale cold air. Now, I don't talk about this a lot in our class, and I will in the next slides, but I just want to remind you from Weather and Climate and Weather Studies Laboratory that the type of a front that we deal with in terms of how we name our front is based on the movement of the cold air, always based on the movement of the cold air, because cold air is more dense than warm air. So when we have a cold frontal boundary, that means that the front is cold because the cold air is advancing. When we have a warm frontal boundary, the boundary is a warm front because the cold air is retreating, not because the warm air is advancing. So this comes down to the fact that at the surface, at any given pressure level actually, colder air is more dense than warmer air. So even if in the warm sector we see that warm air is actually blowing perpendicular to our warm frontal boundary, the reality is that because the warm air is less dense than the cold air to the north, the warm air can't actually move this front. It can't dislodge it. Instead, the warm air is forced to glide up and over this colder air to the north of the warm front. So just keep in mind, and again, I'm going to discuss this in the next few slides, that frontal boundary type is determined by the movement of the cold air. So now what I want to do is I want to focus on a cross-section of this low pressure system. So what a cross-section is, it's a two-dimensional plot, which basically on the horizontal dimension just goes from point A to point B. So in this case, the cross-section starts in the fresh cold air behind the cold front. It actually crosses the cold front, goes into the warm sector between the cold and the warm front, crosses the warm front, and then moves into the stale cold air to the north and the east of this warm front. So one of the dimensions is in the horizontal. In this case, it is a southwest to northeast slice. The second dimension is in the vertical. So just think of this like a big slat that is just basically moving vertically up from line A, B, C, and D. And so if we take a look at what's going on in the vertical, if we go from points A to B, what we see is we have advancing fresh cold air, and the cold front is located right at point B. Now, if we go up from point B, what we see is that as we go vertically upward, the colder air actually leans back to the west or the southwest in this case. So the cold front makes its greatest advance at the surface, and the boundary between the cold and the warm air actually arches back behind the front over the colder air as you move deeper into this fresh cold air and this advancing cold air. Then we move into the warm sector. And by the way, these arrows are meant to indicate the direction in which the wind is blowing in all of these locations. So if we take a look at the cold air, the fresh cold air, we see that the cold air is advancing. This deep blue arrow is actually pushing this boundary along. As we move into the warm sector between points B and C, up here and down here, what we see is that the warm air is now moving toward this retreating cold air at point C, where our warm frontal boundary is located at the surface. And then what you see as we move into the stale cold air to the north and east of the warm front is that, as I said earlier, the warm air, because it's less dense, is actually forced to glide up and over the retreating cold air, which is more dense. And so what this warm air does is it tends to flatten out the retreating cold air. So you can see that the slope of the boundary between the cold and the warm air to the north of the warm front is much more gentle. It's much more gradual. So we have this retreating cold air, and then the warm air is forced to rise up and over the retreating cold air. Now, what I want you to notice, and we'll take a look at this in more detail in a second, is as this fresh cold air advances in the vicinity of the cold front, what's going to happen is this advancing cold air at the cold frontal boundary is actually going to force the warm air in the warm sector to rise pretty abruptly. So the cold air is going to wedge this warm air up. So the cold air is going to force warm air to rise along and ahead of the cold front. We also see that along and behind the warm front, or along and ahead of the warm front, that the warm air is again forced to rise up and over the cold air. So cold air always forces warm air to rise in the vicinity of fronts, always along and ahead of. Now let me just talk about ahead and behind when we're talking about fronts. If you take a look at a front, ahead of a front, when I say ahead, this refers to the area where the front has not yet passed. So it is ahead of the front. Then the front passes, and then once the front has passed, this region here is behind the front. So from B to C, this is ahead of the cold front. A is behind the cold front. From C to D, this area is ahead of the warm front. And C to B is behind the warm front. So just understand that if you're ahead of a front, that means the front is approaching but is not yet passed. If you're behind the front, that means that the front has already passed your location. So what I want to do next is I just want to look a little bit more detail at what happens in the vicinity of a cold and a warm front. So let's say cold fronts first. And if you took weather and climate or weather studies lab from me, you've probably seen this figure already, but it's good review for you to see this again. So what we have now is, again, this is actually kind of a three-dimensional cross-section. So we actually do have a horizontal plane here, and then we have the vertical. So what we basically have is a box of the atmosphere. Here is our cold front basically slicing northeast to southwest. Here we have some isobars kinking along our cold front. Here's the advancing cold air from west to east. And what you see is that the cold air wedges the warm air ahead of it up and over. So just along and ahead of the cold front, we typically see pretty deep cloud development and heavy showers, and if it's in the summertime, not at all unusual to get thunderstorm activity. And we have a couple of cloud types here, and we have some depth of atmosphere over which these clouds are occurring. So let me just give you a couple of notes, a couple of descriptions of what's happening along and in the vicinity of our cold front. First of all, as I said before, it's a cold front because the cold air is advancing. The warm air is forced to rise up by the advancing cold, dense air. And the rising air typically occurs along and just ahead of the cold front. So typically along the cold front and maybe 100 to 200 miles out ahead of the front, and not much further than that. You typically get towering clouds because the angle of uplift is pretty hot, pretty sharp, and so you get a lot of wedging upward of this warm air, so the air tends to rise very rapidly and you get deep clouds. And you typically get intense showers and storms falling from these clouds along a relatively narrow band just along and ahead of the front. And so you guys all know what cumulonimbus clouds look like, and so this is an example of a line of cumulonimbus clouds that are forming just along a cold front. Now let's focus on warm fronts. Now in this case we have a warm front that is advancing from west to east. Or from basically northeast to southwest. You can see the isobars kinking in the vicinity of the warm front. You can see the warm air is trying to advance, but when it encounters the front, when it intersects the front, the warm air is not able to advance any further at the surface, and it's forced to glide up and over the retreating colder air that in this case is to the east. And what we see again is that the slope of ascent is more gentle along and ahead of the warm front because the warm air kind of beats down the cold air that's retreating and it glides up and over the cold air at a much more gentle angle. So what you tend to see are more stratiform cloud formations, and the precipitation that falls along ahead of the warm front typically falls along a fairly extensive shield. And you actually do get a pretty well set of defined cloud types that actually define the movement and the approach of a warm front to your locality. So let me say a little bit more about warm fronts now. They again occur in the vicinity of retreating cold air. The warm air is forced to glide up and over the retreating cold air because the cold air is more dense. You get again extensive stratiform cloud shield along and ahead of the front with a fairly extensive region of precipitation. Now keep in mind that because the air is rising more gently than it is along and ahead of a cold front, that the precipitation is also less intense. It's steady, but it's much lighter typically. And so while it may rain 12, 18 hours ahead of an approaching warm front, the amount of precipitation that accumulates is maybe no greater than it is along a cold front where you get a half-hour heavy thunderstorm. And we call this process by which warm air is forced to glide up and over this retreating cold air ahead of a warm front, we call this process overrunning. We don't have any sort of a technical term for the upward motion that's caused by the advance of a cold front, by the way. We just have overrunning for warm fronts. And again, we get a light shield of light, or a large shield of light to moderate steady precipitation along and ahead of our warm frontal boundary. All right, and let me just kind of show you the cloud types that you'll see in the vicinity of an advancing warm front. Now, the overrunning, let me just show you this. The overrunning, when you're really, really well far to the north or the east of this advancing front, this overrunning, which is basically at its end right here, this could actually precede the actual warm frontal passage by as much as a day. So you can actually begin to see cloud types and cloud formations that begin to appear well before the clouds thicken, lower, and precipitation forms, and then actually have the eventual passage of the warm front. So let's take a look at some of these cloud types. So typically the first type of cloud that you see with an advancing warm front and overrunning are cirrus clouds. Now these cirrus clouds are basically here as a result of the fact that the overrunning air which began at the surface of the warm front at this point has risen really high up into the troposphere, and all of the precipitation has fallen out of it, and all that's left are these very high cirrus clouds. Now, as you move progressively closer to the front, the overrunning air is going to be lower in the troposphere, and the cloud formations are going to differ. So you go from having cirrus clouds to, in this case, cirrus stratus, and you might see some sort of a halo. And as you continue to move closer to the warm front, you'll get altostratus clouds. So these are lower clouds. So again, the overrunning air is lower in the troposphere. As you get even closer to the warm front, you'll get just straight stratus clouds. And then finally, what you'll see is nimbostratus clouds, where you actually have precipitation falling from the clouds as you get closer to the actual warm frontal boundary. So as the overrunning air begins to glide up and over the retreating cold air, this initial rising air has a lot of water vapor in it, and so this is where you get your condensation, your deep clouds, and your precipitation. Now, cirrus clouds can be caused by other factors besides overrunning. So you may see cirrus clouds for other reasons, but if you know that there is the approach of precipitation, if you see in the weather forecast that rain is in the forecast in the next 24 hours and you see these cirrus clouds, you might actually want to just keep an eye on the sky just so you can prove it to yourself and see these cloud types evolve as you get closer to the actual front and the overrunning air becomes lower in the troposphere, and you get these evolving cloud types that lower, thicken, and eventually lead to precipitation. Now what I want to move on to next, and again, I'm just kind of laying the foundation now for talking about the evolution of a mid-latitude cyclone. So I promised that I am going to move back towards this life cycle of a mid-latitude cyclone, but I just want to go through some of the details of what we see with mid-latitude cyclones. So the next topic that I want to bring up is something called temperature advection. Now, advection simply means transport. If you take a look at advect in the dictionary, you'll see that the definition of advect is to transport. So when we talk about temperature advection in the context of meteorology, what we're talking about is the transport of air by the wind of one temperature characteristic to a location with a different temperature characteristic. So what we're really talking about is just advection of air with one temperature characteristic to a location that has a different temperature characteristic. And this kind of sounds a little bit technical or challenging, but in reality, it really isn't. It's actually kind of intuitive. So cold advection is simply the transport by the wind of cold air to a warmer location. So think north wind. Think a cold front comes through and the wind shifts into the north and cold air begins to flow over our location and the temperature goes down. That's cold advection. Warm advection is the exact opposite. This is transport of warm air by the wind to a location that currently has a lower or colder temperature. So if a warm front passes your location and then the wind transports warmer air into your location so that the temperature goes up, that's simply warm advection. So cold advection leads to colder weather, warm advection leads to warmer weather. So the word is a little bit more weighty than what you may be used to, but the concept is actually quite simple and you're probably quite used to it. So let's talk about let's talk about cold advection, warm advection, temperature advection in the context of a map with isotherms. So this particular map, which is from January of 22, this particular map shows basically isotherms at the surface and wind barbs or wind directions and barbs at a number of locations over the United States. And what you'll see is at a number of locations, the wind is actually blowing at a large angle to the isotherms, while in other locations, the wind is blowing much more parallel to the isotherms. Now, when you see wind blowing at a large angle or perpendicular to the isotherms, what I'd like you to imagine is that you're just standing maybe against a wall and your hands are pushing against that wall. The wind is essentially doing the same thing with the isotherm. So when the wind is directed at an isotherm at a large angle, so for instance, very perpendicular to the isotherm, what the wind is doing is it's basically pushing that isotherm along. It's actually moving that isotherm. So if we take a look at this map, we can actually point out locations where there's cold advection in progress, warm advection in progress, and neutral advection where the wind is transporting neither warm nor cold air. So let's look at this in a little bit more detail now. So if we take a look at location A, which I've boxed in here in South Dakota, what you'll see is that the wind is out of the northwest, so it's very important that you remember your wind directions here. This is a northwest wind at 20 knots, and what you see is that the wind is essentially perpendicular to this isotherm, which by the way is the 0 ° Fahrenheit isotherm. So this is a very cold day. And so what we see is that the wind is directed from a region that is colder, where the temperature is below zero, to a region that is relatively warmer, where the temperatures are above zero. So this is transport of colder air to a warmer location. And so what we have going on at A is cold advection. Now if we take a look at B, and now that you see where B is, which is basically Buffalo, it's right at the eastern tip of Lake Erie, you'll see that at location B, and locations in upstate New York, you'll see that the wind is actually perpendicular, in this case to the 30° isotherm, and that areas to the south of Buffalo are warmer than 30, areas to the north of this isotherm are colder than 30. So what you see at location B is that the wind is transporting air. This is a south wind now, it's blowing from south to north. The wind is transporting air with warmer temperatures to a location where the temperatures are colder. So at location B, we have warm advection. Not surprisingly, northwest wind cold advection, south wind warm advection. But you can't always just assume that a north wind is going to be cold advection and a south wind is going to be warm advection. You still have to look at the angle of the wind direction relative to the orientation of the isotherms. So let's take a look at what's going on in Indiana, northwest Ohio, and through southern Illinois into southeast Missouri. And what you'll see is that all of the station models in this area are pretty much parallel to these two isotherms, to the 30 and the 40° isotherms. And so in reality, even though we have winds out of the southwest, even though the winds are blowing at a pretty good clip, 20, 25 knots here, what we see is that the wind is basically transporting air with one temperature characteristic to a location where the temperatures are essentially exactly the same. So in these situations, the temperature advection is referred to as neutral. So the wind is blowing, but basically what it's doing is it's transporting air with one temperature characteristic to a region where the temperature characteristic is essentially the same. So you have to actually look at the orientation of the winds relative to the isotherms to really be able to nail down what kind of advection you're dealing with. And then even though in general north winds give us cold advection and south winds give us warm advection, you can see in this example that strong southwest winds in Indiana give us neutral advection, no advection at all. Now what I want to do next, because this is going to be relevant to your lab, to your exercises, is I want to take a look at the relationship between isobar and isotherm overlays and temperature advection. And I'm going to do that in the next slide. So when we do this, because we're not going to have station models that actually indicate what the wind flow is, if we simply have isobars and isotherms overlaying each other on a single map, we basically are going to have to assume that the winds around our isobars are geostrophic. And that will give us our winds, and we can then take a look at the angle of the wind relative to the orientation of the isotherms. Now, this is not an ideal map. I understand that. I made this map. It's also for the same time as the last map, which is 12Z, the 5th of January, 2022. Now, in this case, what we see are that the blue lines or the blue curves are isobars. So kind of orient yourself, they're isobars. I actually generated this map myself, and unfortunately I was not able to have control over the thickness of these curved lines. So the blue lines are isotherms. The red curved lines are let me start that again. The blue is isobars. The red is isotherms. Let me do it again. The blue curved lines are isobars, and these circle around this area of low pressure that's centered over northern Lake Michigan, and then the red curved lines are isotherms. All right, so orient yourself, and I'll do this with you. This isobar, which is traveling through Arkansas, Missouri, and western Iowa, this is the 1016 isobar. We still use contour interval of 4 millibars, and we're going to move in towards the center of our low. So we go from 1016 to 1012 to 1008, 1004, 1000, 996. So this innermost isobar is the 996 isobar. Now what we're going to do is we're going to assume that the winds are parallel to our isobars. We're going to assume geostrophic flow. And then we're going to take a look at how the winds are blowing relative to the orientation of our red isotherms. So let's take a look at our red isotherms here. I'm going to start in Florida. This is the 60-degree isotherm, 50, 40, kind of curving its way through southern Ohio, 40, 30, you can see the 30 here, 20, 10, 0, minus 10, minus 20. So we have a really wide range of temperatures from the negative minus 20s and the low temperature, looks like it's about almost 30 below right here, to our high temperature, which is 69.6 here. So we have basically a 30 to 70 degree variation, so almost 100 degrees of temperature difference on this map, which is a big variation. Now, let's keep moving. The largest advection is going to occur where the winds are perpendicular to the isotherms. So what I'm going to do is going to actually draw some streamlines to show you the winds around our isobars that surround the low. So here are a couple of arrows indicating wind movement parallel to our isobars. And you can see that in Indiana, Illinois, and into Missouri, that in all of these locations, the winds are pretty much perpendicular to the isotherms. So this is where we have cold advection. Colder air is advancing to regions where the air is currently warmer. On the other hand, if we take a look over here to the east of the low, you'll see where I have these red streamlines or arrows that, again, what we see is that the perpendicular flow is, or the wind flow is perpendicular to these isotherms. It's pushing them along. In this case, warmer air is advancing towards the north where the temperatures are colder. So this is warm advection. In better words, we have the wind transporting air that is warmer to a region where the temperatures are colder. So let me just go back again so I can remove these arrows. And you can again just kind of take a look now and see this parallel flow to the isobars and how the wind is blowing perpendicular to the isotherms. Cold advection in the Midwest, warm advection in the Northeast and southern Canada. So here are our streamlines to show the flow of cold air towards warmer regions here in the Midwest. And then our red streamlines showing the flow of warmer air towards the north, again perpendicular to the isotherms. Warm advection. All right. Now the last thing I want to point out is something called solenoids. So a solenoid is basically a box that is formed by intersecting isobars and isotherms. So you can see the solenoid, these couple of solenoids in Illinois, where we have our cold advection occurring. And then you can see solenoids again in southern Canada and upstate New York, where we have warmer air and warm advection occurring, warmer air moving towards the north. The solenoids are basically used to indicate where the magnitude of the advection is large. So where you have solenoids, you basically have fairly strong flow because the isobars are close together And you have fairly strong temperature advection because the isotherms are also packed relatively close together. And so the wind is very efficiently able to transport air with one temperature characteristic to a region with a different temperature characteristic. Again, cold in the Midwest, warm in the Northeast and southern Canada. And the rule of thumb basically is that the smaller the isotherm is, the larger the magnitude of the advection or transport is. And where you don't have solenoids, so for example, if you take a look at Arizona and New Mexico and Texas, where things look really disorganized, where you don't have solenoids, basically if there is any sort of temperature advection going on, the magnitude of it is quite small. So advection becomes larger when we have solenoids due to stronger winds, because the pressure gradient force is larger, the isobars are packed more closely together, and because you have larger temperature gradients, in better words, your isotherms are packed closely together so that the wind is very quickly and very effectively able to transport one temperature characteristic to a region with a different temperature characteristic. All right, so I know I mangled a little bit of the wording when I described this map, so you may want to go back and look at it a second time, but basically I do go through this pretty well and I do get the concepts there. So make sure that you feel comfortable with temperature advection and solenoids because you will need them for you to be able to complete your questions for the lab or the exercises. All right, let's move on. Now I think I'm finally ready to take a look at something called the mid-latitude cyclone model. Now what the mid-latitude cyclone model does is it basically provides a model that describes the entire life cycle of one of our low pressure systems, from its formation all the way to its dissipation. So the next couple of slides are going to focus on the mid-latitude cyclone model, and I'm going to just basically move from beginning to end of the process. So the beginning of it is referred to as the developing stage. So remember I said that when we have a stationary front and we have basically this buildup of cold air to the north and warm air to the south, that eventually what will happen is we'll get a buckle in the 500 millibar pattern, and we'll begin to get an advance of cold air towards the south. So what we have on the left-hand side, and we have Birmingham, Alabama, basically outlined by point C, is we have a fairly weak low at the surface, and this is located beneath a region of equally weak upper level divergence. So here is a fairly subtle or fairly low amplitude trough. Our vortmax in this case is located, I put it over northwest Arkansas, and I added a trough axis to it. So while you'll see this in your text, the text does not have the trough or the vortmax. I added that myself. Remember that to the east of that the winds are blowing through this wave pattern. So as wind moves through the wave pattern and it moves past this maximum and absolute vorticity, what will happen is absolute vorticity will decrease downwind of this vortmax, and we will get upper level divergence as the vorticity decreases. So we get upper level divergence pretty much over Tennessee. We get our formation of our low over Tennessee where the upper level divergence is occurring, and then we end up getting our counterclockwise and inward directed circulation based on the forces that we discussed in chapter 6. Moving on, if we talk about the mature stage, I have mature stage A, mature stage B, because the book doesn't really distinguish between these next two sets of figures. So this is kind of early mature stage. Here's Birmingham still. And what you see when you have this developing low pressure system is that as we get low pressure forming and we get our counterclockwise and inward directed circulation, what the circulation does is it advects cold air towards the south and the east behind the cold front, and it advects warm air towards the north and the east along and ahead of the warm front. So you can see where these solenoids are located on this particular drawing. All right, so as that occurs, the 500 millibar pattern responds, because if we're advecting cold air behind the cold front, what happens is the mean temperature of the atmospheric column decreases, heights decrease in response to that cooling temperature, and our trough will deepen. Conversely, where we have our strong warm advection, the strong warm advection leads to the mean temperature of the column increasing. As the column warms, our 500 millibar heights will increase, and we end up getting ridging forming, in this case to the north of the warm front over upstate New York and New England. So we end up getting a wave pattern that begins to become better defined as our advection leads to the transfer of cold air to the south and warm air to the north. So trough amplification, sharpening leads to increased vorticity because we have more turning of counterclockwise flow as the air is moving through the trough. We get more or increased divergence downwind of our absolute vort max because the vort max has a larger value, so vorticity decreases more quickly as the air moves out of it, so we get stronger divergence. That stronger divergence means that we're going to remove more mass from the column in this region, and that's going to lead to surface low intensification. So the low gets stronger. And you'll see, if you go back to the previous slide, that we have more isobars surrounding this low than we did on the previous slide. And you'll also see that we have a larger number of isotherms that begin to pack themselves along this low pressure area, with them packing just to the north of the warm front and just behind the cold front. So warm and cold advection around the low also increase in magnitude. And this increase in advection of temperature to the west, behind the cold front and ahead of the warm front, continues to just lead to amplification of our ridges and troughs. And I didn't actually mention this in the previous slide, but I want to actually talk about the tilt of the axis as well. Because as we move through the life cycle of the extratropical cyclone, what we see is that the tilt actually changes its orientation over time. When we're getting formation, so when we're just getting into the early stages of the cyclone model and the low is developing, we'll typically have what we call a positive tilt. So if you go back to the previous slide, and I'm not going to do it here, what you'll see is that the tilt is typically from northeast to southwest, and meteorologists refer to that as a positive tilt. When we have a tilt that is simply north-south, we refer to that as a neutral tilt. And eventually what will happen is we will see our tilt continue to reorient itself in this case, from northwest to southeast, and we refer to that as a negative tilt. Now, the reason that the tilt changes over time is because the rate of advance of the cold air differs from the rate of the decrease, or I should say the retreat of cold air to the north of the warm front. Advancing cold air occurs more rapidly than retreating cold air. So what we'll see over time is that the cold front will pivot around the low more quickly than the warm front will. And some of you already know this. You'll use words like the cold front will overtake, or the cold front will catch up to the warm front. And some of you have seen this before. Now the reason for this again comes back to density. The fresh cold air that we find behind the advancing cold front typically is colder and more dense than the stale cold air that is retreating ahead of the warm front. And so the cold front advances more quickly than the warm front retreats, and as a result of that, eventually what will happen is that the cold front will pivot and get closer and closer to the warm front. Now, as this occurs and the cold air is advancing more quickly than the cold air is retreating in the vicinity of the warm front, what you'll see is the trough will orient itself to show the advance of the fresh cold air, which will be much more to the south and east in this region right here. And so we'll begin to see this pivot of the southern end of our trough axis more to the east than we have to the northern side of it. And that will give us our negative tilt. So if we take a look now at this part, mid-latitude cyclone mature stage B, what you see now is that the vortex is located over Georgia. And if we take a look at our tilt, there it is, there is our negative tilt. So now you can see that the trough axis is tilted negatively from northwest to southeast, indicating the very rapid advance of the cold air on the south side of the low. So again, we get our trough amplification. Sharpening is going to continue to lead to increased vorticity, greater divergence, more intensification of the low at the surface. You can see more isobars closed off, more isotherms, more solenoids, and so you just see this continual intensification of the low at the surface. And again, I want to note that the cold front is pivoting around the low more quickly than the warm front is. And this figure really doesn't show that, which is unfortunate. It doesn't really illustrate this pivot. But I really want to point out that that is what happens. So we get this continual deepening of our 500 millibar trough. We get this continued building of the ridge, which we don't see off to the east. We continue to get intensification of the surface low. Our warm and cold advection continue to increase in magnitude. And then we get our negative tilt of our upper level trough. Now, what we see over time, because of this pivot of the cold air around the low and the cold front around the low, is that we go from having this positively oriented trough at the beginning of the process to this negatively oriented trough later on. And the reality is that as the cold air is pivoting around the surface low more quickly than the warm air is, what we see is that basically the warm sector between the cold and the warm front begins to get squeezed. And the center of the low at the surface increasingly becomes surrounded by cold air. Now, if the low is surrounded by cold air, what we see is that the atmospheric columns surrounding the low also become increasingly cold and the heights lower. And so as this occurs, what you'll see is that we may actually begin to get a couple of closed isoheights at 500 millibars. So we'll begin to get, remember I used this term a couple of chapters ago, we'll begin to get a cutoff low. We'll begin to get a cutoff low, and what we see at the surface is that the cutoff low and the surface low tend to become vertically stacked. So over time, the surface low and the cutoff low will become oriented pretty much straight up and down. So the cold front pivots more rapidly around the low than the warm front. The warm sector shrinks, and conversely, the cold sector expands. The surface low is increasingly surrounded by cold air, and then the surface and the upper lows vertically stack. Now, at this point, things typically look pretty impressive at the surface. You can see we've got a pretty intense set of isovorts surrounding this vortmax at 500 millibars. Typically at the surface, the low will be surrounded by a very large number of circular isobars and really well-defined fronts. And so things will look really, really impressive. But the reality is that as this 500 millibar pattern begins to close off and we get this vertical stacking of the upper level and surface lows, the reality is that the low is actually nearing the end of its life cycle. It's actually getting close to the point where it's reached its maximum intensity and is going to begin to dissipate. So let's look at this. When we get to the dissipation stage, what we see is that our surface and our upper level lows are pretty close to being vertically stacked. And in fact, this figure doesn't show it nearly as dramatically as it actually occurs in the real world. It is not at all uncommon in the real world when a surface low is dissipating for the low at the surface and the 500 millibar low to literally be right on top of each other. All right, so this actually shows a little bit of offset, but in reality, you can get perfect vertical stacking. So here's our upper level low with a couple of closed isoheights. Here's our vortmax with our isovorts surrounding it. And what we see at the surface is a low with now an occluded front. We haven't talked about occluded fronts yet in this class, and in fact, I really don't talk about them very much in weather and climate. I think I do go into a bit more detail in Weather Studies Lab, but this is an occluded front. An occluded front forms when a cold front literally overtakes the warm front at the surface, and so what happens is that where this happens, and it's always closest to the center of the low, the warm sector is completely squeezed out, and you can see the warm sector is displaced to the south and the east, and so the surface low is surrounded by cold air now, which we then see by these closed circular isoheights surrounding our upper level low, which marks the location of the lowest 500 millibar heights, which means that this is where our coldest columns in terms of average temperature are located. Remember that upper level lows mark where the coldest mean temperature of the columns are located. So now the surface low is surrounded by cold air, the warm sector is squeezed off to the south and the east, and the merge boundary basically will show us this occluded front. It's still a boundary. Typically you still have fresh cold air here to the south and the west of this boundary, and you still have stale cold air to the north and the east of it. So you will still get a temperature difference across this boundary. It's just that the warm sector has been completely squeezed out. So we get an occluded front, and we get these closed upper level isoheights. And what happens is, in the region where our surface low is located, assuming we actually have perfect vertical alignment, is that there's literally no change in vorticity over this area. So if there's no vorticity change over the upper level, over the surface low, so at 500 millibars, the vorticity stays the same because everything's just moving around in a circle. What happens is we lose our upper level divergence over the surface low. And so what happens is we continue to get convergence at the surface because we have pressure gradients at the surface. So we add mass at the surface. We lose our divergence at upper levels, and as our upper level divergence approaches zero and surface convergence continues, the column mass will increase and the low will begin to fall apart. It will dissipate as the weight of the column increases. Now, what we'll see as the surface low dissipates is that we have a triple point right here. So the triple point is where the occluded front, the cold front, and the warm front meet. And typically what we'll see over the triple front is that, or the triple point, is that this is a region where we have a lot of divergence, where we have decreasing vorticity. And so often what will happen is the initial low, which meteorologists refer to as the primary low will begin to fill and dissipate as pressure increases over this area, and low pressure will form over this triple point, or at this triple point, and meteorologists will refer to that as a secondary low. So the primary low will fall apart, a secondary low will form, and it will take over. And then the entire process of the mid-latitude cyclone model will repeat itself, starting with low pressure at the triple point. So here's another example of the dissipation stage. Here are surface and upper level lows, and in this case, the book has actually put them a little closer to each other. Here's our vort max, here's a triple point, and in reality, the divergence maximum will begin to fall apart here and will begin to maximize over the triple point, and we'll get secondary low pressure development at the triple point over time. So the cold front overtakes the warm front, the merged boundary becomes an occluded front, the upper low closes off, so we'll get a cutoff low right here. Upper level divergence will approach zero over the primary low, and then surface convergence will continue in the primary low, which will cause it to fill. In other words, pressure will increase as we add mass at the surface. And then as the surface low dissipates, we'll get secondary low development at the triple point. Okay, let's keep moving on here. A couple more characteristics of what's occurring in the vicinity of our surface low pressure system. And I want to go through this because I want to talk, this part focuses on how low pressure moves over time. So if we focus on our low, what we have here is basically a representation of a mature low where we have well-developed warm and cold fronts. We can see the cold front is beginning to pivot. You can see this bowing of the cold front. So the cold front is beginning to pivot around the low more quickly as it approaches the warm front. And what we see that as this process is occurring, the movement of the low basically will be towards where we have our largest negative pressure tendencies, where pressure is falling most rapidly over time. Now, we don't really talk about station models in detail in our class because I go through it in Geography 1250 and 1260. But a pressure tendency is a measure of the change in pressure over the previous 3-hour period. And where we have large negative pressure tendencies, that basically means that the weight of the atmospheric column is decreasing most rapidly in that region or in that location. So this is where the largest upper divergence is occurring. So you can see here we have a couple of isolines of pressure tendency, and here we have a -2 millibars in 3 hours pressure tendency isoline. So this is where upper level divergence is increasing most rapidly, and therefore if we drew an arrow to where the low is moving, it would move from its current location right into the circle where we have that -2 millibar per 3-hour isoline. So this is where we get our low movement over time, where we have our largest negative pressure tendencies. Now, we get our largest negative pressure tendencies where we get our greatest increase in upper level divergence. So this is where we're going to have decreasing vorticity at this time. Also, it's where we typically tend to get our strongest warm advection. Now, I want to say something here because the book doesn't do a good job at this particular location in its discussion. Just because the temperature advection is warm, just because the density of the air is decreasing because it's warming, doesn't mean that the pressure is decreasing for that reason. Warming air expands, but just because air expands doesn't mean that its weight decreases. A warming column doesn't get lighter. it becomes less dense. The weight of the column from the top of the atmosphere to the surface will not change. So warm advection doesn't cause the weight of the atmospheric column to decrease. It just happens that where we have our largest negative pressure tendency also aligns with where warm advection is occurring. So I want to make that really clear. Temperature advection doesn't make the weight of the column change. It makes the density of the column change. All right, and then the low moves northeast to where we have our largest negative pressure tendencies. Now, if we talk about high pressure, it's pretty much the exact opposite. Here we show our low moving off to the north and the east, and what we see now is that our high, in terms of its movement, is going to follow the largest positive pressure tendencies. And so we see in this case an example of a 2.5 millibar in 3-hour positive pressure tendency behind the cold front, located right here. And again, what the book does, it implies that this very strong cold advection makes the column weigh more. And again, that is not correct. The strong cold advection makes the air in the column more dense, but it doesn't change the weight of the column. Getting colder doesn't add mass to the column. Getting warmer doesn't take mass out of the column. So what we see here is that the largest positive pressure tendencies occur in a region of strong cold advection. But again, I just want to make clear that that cold advection, while it increases the density of the column, doesn't change its weight. So the movement of the high pressure follows the largest positive pressure tendencies. This is where we tend to get our largest upper level convergence, so where we have strong, rapid increases in absolute vorticity at upper levels. And again, where we get our strongest cold advection at the surface. And so the high moves to the southeast. Now the last little bit that I want to talk about is the vertical motion and movement of air around a low. And so this is a principle that refers to conveyor belts. So conveyor belts basically talk about large belts of motion or movement of air. And what we have in this particular upper part of the figure is something called a warm conveyor belt and then a cold conveyor belt. So let's focus on our low at the surface. Here's the low. We have a cold front. We have a warm front. Keep in mind that we have our counterclockwise and inward moving circulation at the surface. So what we see in the warm sector is that we have warm air that is advancing toward the north in our counterclockwise circulation at the surface. It intersects the warm front and then is forced to glide up and over the colder air to the north of the warm front via overrunning. So what the warm conveyor belt basically does is it basically takes our overrunning air and it turns it into a nice big arrow. And so you can see the warm air advancing towards the north, intersecting the warm front, and then gliding up and over the retreating stale cold air to the north. All right, so that is what our warm conveyor belt is showing. The cold conveyor belt is basically meant to show the movement of the stale cold air to the north of the warm front. And what you would see, in fact, is that the movement of the air would be out of the east, southeast, or even a little bit northeast. But what happens is this cold air that starts at the surface, basically what it's doing is it's being forced to glide up and over the stale cold air that's to the north of the warm front, and then it actually will curl around and to the north and the west of the low. But if we were to take a look at this in the vertical, what we would see is that the warm conveyor belt actually ends up being higher than the cold conveyor belt. So the cold conveyor belt actually undercuts the warm conveyor belt, even though both of them are rising in the stale cold air to the north of the warm front. So the warm conveyor belt, let me just give you a couple of characteristics. Basically, this defines the overrunning clouds of precipitation that occur to the north of the warm front. As the warm conveyor belt air moves higher and higher up, as it moves further north of the warm front, it will end up being integrated into the westerlies at the upper levels, and you'll typically see the warm conveyor belt kind of turn from being southerly to southwesterly. And so it kind of takes on a little bit of an S shape, the upper part of an S, as you move further north of the warm front. The cold conveyor belt air, again, starting at the surface, it glides up and over, again, the stale cold air to the north of the warm front, but it undercuts the warm conveyor belt. It glides over the fresh polar air then to the north and the west of the low center. And typically what we'll see is that, and you can see this kind of depicted here, to the north and west of the low center, we typically will get a region during the wintertime of pretty heavy snow falling out from the cold conveyor belt air that is rising to the north and the west of the low. The limiting streamline, which we'll see in the next figure, the limiting streamline basically is the western edge of the warm conveyor belt. So this basically is the western edge of where we have warm air rising with our warm conveyor belt. It typically aligns with the advancing cold front. So it typically is aligned with the cold frontal boundary. If we take a look at a couple of satellite images so we can actually see what these conveyor belts look like on a satellite image, this is a visible satellite image of a very mature exotropical cyclone. You can see, actually, if you take a look at the texture of the clouds, you can actually see higher clouds to the east, right here, lower clouds to the west. You can see the edge between the higher clouds, the lower clouds, and you can actually see where the cold front is located, where we are at limit, where the air is no longer rising, right here where my cursor is. So if we take a look to the west, we put in the conveyor belts, the low and the front. You can see the warm conveyor belt in this thick band of clouds along and ahead of the cold front. Then it glides up and over the cold air to the north of the warm front. So all of this is warm conveyor belt air. And then it gets turned to the west by the upper level westerlies as the warm conveyor belt air ascends to a higher level in the troposphere. The cold conveyor belt is undercutting the warm conveyor belt, and these are the cold conveyor belt clouds that are coming out from beneath the warm conveyor belt to the west of the warm conveyor belt. So you can see this line right here that separates the higher clouds of the warm conveyor belt from the lower clouds of the cold conveyor belt that basically come out to the west. And then you've got your limiting streamline, which is where our cold front is located. So again, you can really see once you put the low and the fronts on this satellite image where the warm and the cold conveyor belts are located, where the cold conveyor belt clouds come out from beneath the warm conveyor belt clouds, and where our limiting streamline and the cold front are located. So warm conveyor belt clouds, overrunning clouds steered by upper level winds, right here. Cold conveyor belt clouds undercut the warm conveyor belt. You can see them coming out here to the west of the warm conveyor belt. Glides up and over the fresh polar air to the northwest of the low center, and again, we typically will get a lot of snow here in the wintertime. And our limiting streamline, again, oriented pretty much with the cold front, and it is the western edge of the warm conveyor belt. All right, just a little bit more about one last conveyor belt, and this is called the dry conveyor belt. The dry conveyor belt, you'll see this pretty well on vapor images, and typically what will happen is when you're getting convergence in the upper part of the troposphere, so this is typically associated either with a jet streak or basically in the upper troposphere when you are finding yourself to the east of a vortmin, as you get increasing vorticity in the tropopause, you'll get converging air. This air will then sink into the middle troposphere, and then it will get integrated into the middle tropospheric flow like this. So this is typically sinking air from the upper troposphere where you have convergence of dry air into the middle troposphere, and typically what will happen is this dry air will kind of get integrated into the middle level circulation, and you'll see it really as an intrusion of very dry air into the cloud pattern on a satellite image. So dry air descends from the tropopause into the mid-tropospheric trough, and then what you see is this dry air basically getting folded into the circulation. Now, this is a vapor image. So this basically shows our dry conveyor belt, where you see this darker area right here. This indicates that the top of the vapor layer is lower where our dry conveyor belt is located than it is in this part of the circulation around the exotropical cyclone. So here are examples of warm, cold, and dry conveyor belts. And again, this, in this case, is an infrared image. So we've got one big, very mature exotropical cyclone off the coast of Canada. We have another one in the northern Pacific right here. And you can see what meteorologists will often refer to as this comma-shaped cloud. Now, this is obviously not a single cloud, but you can kind of see this comma shape to it. So if we take a look at this low that is off the west coast, you can see the higher clouds that are to the east. These are our warm conveyor belt clouds. You can see this very sharp edge right here, and this distinguishes from the warm conveyor belt clouds to the cold conveyor belt clouds that are coming out from beneath the warm conveyor belt. And then you can see this very obvious area of dry air just swirling into the circulation. It's almost like a jelly roll of dry air that's swirling in. And the upper level low is actually located right here where my cursor is. So really well developed upper level low. And then you can see the same thing going on further west into the North Pacific. All right, so you can see it very, very well. Just focus on this one that's further east, warm conveyor belt, cold conveyor belt, and then you can see the edge between the warm and the cold conveyor belts. Here's the limiting streamline, which is the back edge of our warm conveyor belt, and this would be where our cold front is located at the surface. And then finally, the dry conveyor belt descending from the upper troposphere, and then again folding into the circulation and getting swirled in to show this sort of an image. All right, we're at the end of chapter 13, and here are the lab questions for my distance students. So here are the questions that you need to complete to finish off your lab for the week. Now remember, this is not the assignment for the face-to-face class if you happen to be a face-to-face student watching this video. This is the assignment for my distance students. If you have any questions at all, distance students, about anything I've said here, by all means, please post a question to the discussion board, or feel free to ask me live during my office hours on Zoom. And if you actually understand what's going on and you know the answers to the questions that your classmates are posting, please post your answers on the discussion board as well. Remember, all of this counts as participation. But that's it. That's all for chapter 13. I'm going to end this video now. I will post it on YouTube, and you will see an announcement pop up on our Canvas site when it's ready for you to view.